purpose of this video is to give you some hints about how to handle the two-dimensional kinematics lab. So first of all, what I would do is read through the background here. Gives you a bit of an idea about how they're getting some of these equations, and I'll show you how to handle the math in these equations in a little bit. It's not quite as bad as it seems initially. In the procedure section, it tells you a bit about the catapult and points out some of the features. You've got this release lever here, you've got this winch, then you've got the bucket here where the ball goes. It says at the beginning that what we want to do is set the distance of the catapult from the bucket. The bucket's over here. There we go. There's the bucket. As being 37 meters from the wall, 68 meters from the bucket, and we can do that by moving this around. And it could be moved. Let's see. We need 37 meters from the wall. There we go. So this is fairly important. You don't touch the winch or anything until you've put the ball into the bucket. What you'll find is this: if you start trying to muck with this while the ball is not in the bucket, it actually moves the catapult. So you do this, and it says place the ball. Please place the ball in the catapult first. But then you see it's actually moved it. So that's a bit of a problem. So just take the ball, put it in the bucket first, and then you can mess with it. So what it says to do is, well, we'll just try it without changing the winch setting here, and you'll see what happens. We hit the thing here, and you see it doesn't go very far, right? And that's because we don't have enough velocity. All right, so we can drag this back. Again, we'll pick up the ball. Oops. Pick up the ball, put it in the bucket, and now we can adjust the velocity. So now I will push the velocity all the way to the top. And the important thing is you need to be able to count these numbers, this number of bars here, because that's what's going to go into your report once you figure out how far to put it. So I'll see the bucket here. Let's see how this goes. And away it goes. Whoa, it's a bit far. Alright, so that would tell me that I needed to not put it up quite as high. So just be aware of that. That's the only thing you need to be able to do. Then it says later on to move it again, 44 meters from the wall, 75 meters from the bucket, and you'll try it again and go through the same process. So this is the report that you'll have to fill out. You'll notice that the wall distance and everything else and the catapults, it's already there. All you have to record here is the number of bars, and that's in the velocity counter. And then it has some math here that you'll need to do in order to calculate launch velocity. So what I want to do is give you some guidance on how to do that. Now what I'm using here is a calculator. This calculator is actually part of Windows. If you've got a Mac, they have a similar app as well as part of the Mac package. Let's turn this back to this is a standard view. This is what you see initially. But if you change this to scientific, you'll get all these other different functions, and you'll need some of these in order to get this result here. All right. So for this question here, where it asks for the launch velocity needed to land the ball into the bucket, you need to be able to put in the information that's in the question. Now the R is from the actual data. That's the distance from the bucket to the wall, and the distance from the catapult to the bucket, and that's what you'll get from the lab results, and you'll be able to input that yourself. Now the G is 9.81 meters per second squared. That's the acceleration due to gravity. And then you've got this YF and YI, and those are given here in the question: 2.5 for YF and 9.59 for YI. Now the angles here, the cos theta, if you've never seen this before, it's actually not that hard to calculate if you've got a calculator. So if you've got 27.5 degrees and you wanted cos theta, what you do is you do cos 27.5. Now if you do that, you'll do it in the calculator up here. You put 27.5 and you hit cos, and there you go. So just take it to 3 decimal places, that'd be 0.887. And that's the value that goes down here. If you wanted tan theta or tan theta, it's the same thing. We do tan 27.5. It's going to give a different result, of course, but it's okay. And we get that here. We just clear it out. And we type in 27.5 again. And we hit tan. There we go, 0.520. And of course, that's what goes in here. So when you're doing this in your calculator, you probably want to get these values all separately and do whatever's in the parentheses, get a result for that, and then multiply that by 2, and then get a result for that, and take 9.81 and divide it by that result, then take the square root of that result, and then you can have the r and the cos theta here. Now keep in mind the r is also down here as well, and don't forget to include that in that part of the expression as well. So once you have all that, you know how to calculate a cosine and a tangent, then it's just a matter of putting those pieces of information into each equation. And like I said, take it one step at a time. Do r times 0.520 minus the 2.5 minus the 9.59, and do that first before you do the rest of it here. Then you'll be doing a similar equation here. This is to get the range, and you've got some information already from the problem. You've got your VI, which is the initial velocity, and that's going to go in these spaces that I'm showing you here, and that's going to be 30. And then you need the VI squared. Now to get that, what you'll do is you'll just take the VI squared is equal to, is equal to 30 squared, which is equal to 900. Now you can do that in your calculator as well. To do a square, you do this, and then hit x squared. There you go. So that's for the VI squared. Now the sine theta is similar to what we did up here. So let's do that one. So it's sine, and again it's 27.5 degrees. So we'll put that in there, and we get that value to 7.5, and hit sine, and it's 0.462 when we round it. And if you wanted sine squared, we do what we just did with the square value up here. And it's going to be equal to 0.462 squared, which equals 0.213. So that's what goes into this value right here. And the one that goes into sine theta is 0.462. The G value is 9.81, and you'll see it there as well. Alright, so again, take it one step at a time. Do this one squared first, and then multiply it by this one, and then get a result for that. and then get a result for this, multiply it by g, multiply it by 2, take this, add this to this. So just take it one step at a time, and you'll end up getting the right answer at the end. So be sure to show all your work so that I can give you partial credit if you do end up not doing so well with the math on these particular examples. So if you can handle those, you should be able to handle anything else that's being asked of you in the lab report. Let's go take a look at it. So we've got the questions here, which I was telling you about, and then this question here is very much related to this one up here, except now you've got different data, so you just plug in the different data. So that'll see if you understood what you needed to do there, but the g value is going to be different because it's on Jupiter, and then you can change the other pieces of data that need to be changed in order to get the right answer for this problem as well. Alright, so that's pretty much it for that.